Good morning. I'm Wei from Lumen Labs. My topic today is assessing the efficacy of filtered Far-UVC in high-risk hospital space. So, a little bit about the research background. Lumen Labs, in collaboration with China CDC, tested the efficacy of Far-UVC in 20+ in situ space in 5 Tier 1 hospitals across China. These are the hospitals in Shanghai, Beijing, and Shandong provinces. So the study utilized continuous active air sampling to more accurately measure microbial contaminants in real time. These are the high-risk spaces that we picked. They are transfusion room, changing room, ICU, CT room, dental clinic, fever clinic, etc. The setup, the irradiance simulation that we use dialects for safety and uniformity. The irradiance and the ozone verification we do after equipment deployment. The uniformity is very important, especially in the high-risk environment. The peak irradiance over average irradiance, it should be equal or less than 2. And Far-UVC irradiance measured from 1.9 meters from the floor should be less than equal to 5 microwatt per square centimeters. And that is equivalent of about 144 millijoule per square centimeters per 8-hour period. That's less than the TLV, newly advised TLV for ACGIH for eyes. And the average flux, this is an interesting number, is we take the total energy of Far-UVC in the space divided by the volume in the space, is about 5.6 milliwatt per cubic meter. Sampling. We do active sampling only. Use 6-stage Anderson sampler to simulate human air tract. And these samplers are placed normally in the center of the space, 1 meter from the floor, with a flow rate of 28.3 liters per minute. And we do 10 minutes sampling. And continuous. We do samplings typically 9 times a day, from 8 a.m. to 4 p.m. during normal hospital operating hours. And the petri dishes taken out from the sampler, put into incubator for 48 hours period at 36 degrees C environment. And the colony forming unit is on the petri dish is calculated, is counted, and the CFU per cubic meter is then calculated. We do, for each space, we do 4 days test, 2 days with Far-UVC on, and 2 days with Far-UVC off. Results and data. In a transfusion room in Zhongshan Hospital in Shanghai, a 43 square meter space. With the use of Far-UVC, the average CFU was reduced from 312 to 106. So day 1 with 222 off, so it's a control day. There's an air sanitizer on. This is an interesting point. It's a 254 with circulating air. As you can see, there's pretty big fluctuation of CFU during the morning rush hour and the afternoon peak. Day 2, we turn on the 222 and still leave the air sanitizer on. As you can see, the CFU is much less, and the peak has been flattened. Day 3 is, again, a control day. We turn off the 222 and we also turn off the air sanitizer. As you can see, the fluctuation come back, the peaks in the valley. And day 4, we again turn on the 222 and turn off the air sanitizer. And as you can see, as expected, the CFU is much reduced, and it's a much smoother curve. And with the use of 222 in this particular space, as with a baseline of 5 ACH exchange per hour, we estimated that Far-UVC added about additional 9.7 EACH according to this formula. And some more results and data in other spaces, CT, nurse station, infectious disease ward, dental. In all cases, you can see the red lines are without Far-UVC, the green lines are with Far-UVC. The results are very similar. The Far-UVC is very effective reducing the CFU in the air. So in the Zhongshan Hospital, for the A spaces that we tested, if you take all of them as average, the average CFU go from 272 to 96 with the use of 222, and the reduction rate is 65%. The peak CFU went from 622 to 163, and a reduction of 74%. And this is the data from the Zhongshan Hospital trial. And again, the average irradiance per cubic meter is 5.6 milliwatt. So, future testing. We're going back to the same hospital for more testing. This time we're going to do longer duration, from 2 days to 5 days. From sequential only to sequential and parallel. And higher air sampling height. We're going from 1 meter to 1.5 meter to better simulate the human breathing zone height. And the petri dish nutrient going from agar plate to blood agar plate to capture more bacteria. And we're also using occupancy center counter to count people coming and going. And we're targeting July completion, and we'll publish data in August. So really soon. Look forward to that. And so with result like this, very good result, great reduction in CFU. Why isn't Far-UVC more widely adopted? I have three reasons. Lack of awareness, and also people's the bias against UV, and also lack of regulation in the US. The recent NC standard and the UL standard 8802 is very helpful. China is also rewriting its UV standard, but CE is coming slow for Europe. And the third reason is very high cost. So on the right, I have a chart of Far-UVC cost. These are what the user pay per milliwatt. Back in 2021, when Far-UVC was first introduced, is about $30 per milliwatt. So for a 20 square meter room, the estimated cost to achieve good result, 5.6 milliwatt per cubic meter, is about $9,000. It's really very, very expensive. And today, the cost is much better, much lower. It's about $10. This is what the user pay. And so for that same room, it's about $3,000, much better, but still very expensive. We are working on technology that will greatly reduce the cost of Far-UVC. We predict in 2 years per milliwatt cost for Far-UV, filter Far-UV, will be $3, and by 2028, it will be $1 per milliwatt. And that's, I think that's a very important milestone. So that, which means for a 20 square meter room, the cost the user pay is about $300 US. That's similar to commercial lighting. So the key to wide adoption of Far-UV is follow the Moore's law, relentlessly drive down the cost. And be continuous. We believe in continuous disinfection. So the Far-UV should always be on when the room is occupied, when there's people around. And be isotropic. We don't believe in spotlight. We believe lights that are widespread, isotropic, that cover the entire room with low intensity. for safety. And very important, longer bulb life, in thousands of hours, maybe in one day exceed 10,000 hours. And replaceable bulb. I know EU is working on policy that mandate replaceable light source in a couple of years. So Far-UV should be the same, should be replaceable bulbs. This is our product family. There's wall mount, ceiling mount, tabletop, and a wide array of products available from Luminabs. A little bit about us. Luminabs is a original equipment manufacturer OEM dedicated to create filter Far-UV based solutions. We have developed innovative proprietary Far-UV bulb, filter, driver, and fixtures. Founded in 2020, 4 years ago, by FES International, which is a contract manufacturer with 20 plus years history. At the core of it is Center for Advanced Optics, which is the R&D center of both FES and Luminabs, located in China and the US, with manufacturing center in Thailand and China, with global sales and distribution. Questions?